Next, we have further discussion about electromagnetic wave characteristics. And before this, we have previous electrostatics, magnetostatics. All lectures are available. So go and visit in the playlist, okay, and subscribe the channel. Now we are going to see Poynting theorem. What is the statement of the Poynting theorem? And we'll see what is the Poynting vector. Two things we are going to see. And here, along with the statement, we are going to derive the expression that will satisfy the Poynting theorem. So that a statement says that the net power flowing out of a given volume is equal to the time rate of decrease in the energy stored within the volume V minus ohmic losses. So how much energy is coming out from this particular volume is equal to the rate of decrease in the energy minus ohmic loss. So here if you see in this diagram, here we have, this is the power coming out from that volume, and this is the energy stored, okay, that is electrical energy, and here we have magnetic energy that is also stored. So this is decrease in these two energy minus here what we have ohmic loss, that is equal to the power coming out from the surface. And from the energy conservation, you know that energy neither can be created nor destroyed. So here that power in will be equal to the how much energy is being stored, how much energy is being dissipated. Okay, all these considerations are there. So finally, this energy can be transferred from one point to another point by the help of electromagnetic waves. So already we have discussion electromagnetic waves equation we have in a space domain. Then we have utilized the time varying constant. So by the help of time varying concept that we are multiplying with e to the power j omega t. On the basis of that, we got that how electromagnetic waves are going to propagate in particular medium or in different mediums. So that rate of transportation when this wave is going to move from one place to another place. So that we are going to utilize the Maxwell equation. So by the Maxwell equation, earlier we have del cross E equal to minus dou B by dou T. And B is what? Mu H. So that's why we have minus mu dou H by dou T. B is what? Mu H. Mu is the permittivity. Okay. So finally, here we have B equal to mu H. One is the epsilon and that is the mu. One is the permittivity, one is the permeability. Okay. So epsilon is the permittivity, mu is the permeability. So del cross E equal to minus of this we have, and another expression we have earlier about del cross H equal to J plus dou D by dou T. So J is that is the current density, conduction current density, and D is the flux density, electrical flux density, and D equal to epsilon E. So that epsilon is permittivity, mu is the permeability. So that's why we have equation 1 and 2 here. Now we are taking the dot product of the equation 2 with E. So finally here we'll have E dot del cross H. So finally sigma E square, and J is the conductivity, that is the sigma E. So here we have sigma E square plus E into epsilon dou E by dou T. Now to explain this LHS, we are going to utilize the identity where we have two vector A and B. Then we have relation del dot A cross B equal to B dot del cross A minus A dot del cross B. So here what we see that this is the first term of this expression. So finally we'll have in place of A we have H, in place of B we have E. So we are able to write this expression, okay, this equation 3 with the help of equation 4 can be written in this format, okay. So finally LHS is going to become H dot del cross E plus del dot H cross E, and RHS will remain same what was in equation 3, sigma E square plus E epsilon dou E by dou T. Now this sigma E square first term, and now this dou E by dou T we can write in this format. Okay, since differentiation of dou E square by dou T is what? This is going to be 2E dou E by dou T. Okay. So finally, this term is equivalent to this term, same. So again, now by dotting the another equation that we have equation 1 with H. So we have H dot del cross E equal to H dot minus mu dou S by dou T. Okay. So finally it can be written as, after rearrangement, we'll have here minus, okay, mu. So again, if you see the differentiation of this, what we'll have here, 2 dou H by, so this H square is here, okay. So finally 2H dou H by dou T. So this 2 will be cancelled. We will have minus mu H dou H by dou T. So that is the similar expression what we have here. So this equation 6. Now again, similar situation we are going to use here. So now we have equation 5 and 6. So here we got the value of H dot del cross E. So this equation 5 LHS first term will be replaced by this equation 6 RHS. So we have minus mu by 2 dou H square by dou T minus del dot E cross H equal to sigma E square plus 1 by 2 sigma dou E square by dou T. So now we are going to rearrange and taking the volume integral of this equation number 6. So finally, that volume integral of del dot E cross H dV equal to minus dou by dou T volume integral of 1 by 2 epsilon E square plus 1 by 2 mu H square dou V or dV minus again volume integral sigma E square dV. So this equation 7. So here what we are seeing that we have volume integral. So now we are going to use the divergence theorem that we are going to apply to the LHS, since divergence theorem is going to give the relation between the volume integral and the surface integral. That expression is what? That volume integral is here in the equation 7 LHS. So finally the relation is what? The surface integral of any vector, surface integral of any vector over the closed surface is equal to same as the volume integral of the divergence of that vector. This is the divergence theorem. So here in place of A, what we have? E cross H. So that's why by applying the divergence theorem, that equation 7 and equation 8, that LHS what we are getting here, both are equal. So that's why equation 7 can be written as surface integral over the closed surface E cross H dot ds equal to minus dou by dou T volume integral half sigma E square plus half mu H square dV minus volume integral sigma E square by square into dV. So this is the equation 8. So finally this LHS is the total power leaving the volume. How much power is going to leave this volume? And this first is the rate of decrease in the energy stored. So this first one is the electric field component, second is the magnetic field components. So that is going to decrease. And finally this component is the ohmic loss, which is being dissipated in the form of heat. Okay. So finally, this equation 8 is going to satisfy the Poynting's theorem statement, or like this we are able to prove the Poynting's theorem. So this is very, very important questions especially for the university exam, as well as this concept can be utilized for the solving the competitive exam questions. So here we have seen rate decrease is happening inside the volume and power is leaving the volume, and another decrease is happening indirectly, that is the ohmic loss. So finally total power what is going to leave the volume is equal to rate of decrease in the energy stored. The energy is stored in which form? It is stored in the form of electric and magnetic field with the help of electric and magnetic field. So we have electric energy and magnetic energy, both are going to decrease here, and another is it is being dissipated in the form of heat. And another important concept is maybe you have one mass also, Poynting vector. So the quantity E cross H is called as the Poynting vector, and its unit is Weber per meter square, and it is normal to the both E cross, that is E electric field and magnetic field. Okay, so that direction is AK, AE cross S. So if electric field and magnetic field both are going to lie in the X and Y plane, then direction of this pointed vector is along the Z axis. So if you have any doubt, you can write in the comments. Okay, I'll reply those questions. So share with your friends also. Subscribe the channels, like it, and feel free to write any comments, whatever is there. Okay.